Hello friends, welcome in a lecture of fluid mechanics subject. Myself Mitesh Patel. I am a assistant professor in a mechanical department at the Dr. Subhas Technical Campus, Junagadh. Today's our lecture topic is a dimensionless numbers. So in this lecture we elaborate all numbers and its importance and how to get a mathematical equation for all types of dimensionless numbers. Okay, so let's start the lecture. First, we see the what is the dimensionless number. Number is the just ratio of two forces. Dimensionless number are obtained by dividing the inertia force by the different forces like a viscous force, gravity force, pressure force, surface tension force or elastic force. So in short we can say that dimensionless number is just a ratio of forces in which inertia force ratio is a inertia force to different forces which are discussed earlier. Okay. The important dimensionless number which are very important for a model analysis is the given below. It's a 5. First one is the Reynolds number. Second one is the Froude's number. Third one is the Euler's number. Fourth one is the Weber's number. And fifth is a Mach number. Okay. So let's see the all details and mathematical equations of all these numbers. So let's start. First is the Reynolds number. Reynolds number is the ratio of two forces. We know that first one is the inertia force of flowing fluid to viscous force of fluid. So Reynolds number is the ratio of inertia force to viscous force of fluids. Okay. The expression of Reynolds number is obtained as follow. Okay. Let's see. Inertia force, we know that how to get the inertia force, mass into acceleration of a flowing fluid. Okay. So we get the value of mass from the equation of density. So value of mass is a density into volume. Okay. Now we know the acceleration's equation. Acceleration is equal to velocity per unit time. Okay. Or velocity per time. Okay. It's called the acceleration. Okay. Now rearrange the equation. The time is shift from the velocity to volume. Now volume per unit time is called the discharge. Volume per second or volume per unit time is called the discharge or flow rate. So we know that the equation of flow rate, area into velocity. So put the value of discharge or flow rate volume per unit time instead of volume per unit time. We can write the area into velocity, A into V. So density as it is, velocity is a V, and volume per unit time, it is a flow rate, and its equation is a area into velocity. So put the value at here instead of volume per unit time. Okay. Now the equation is a rho A V square. Rho A V square is the equation of inertia force, and inertia force is defined by the Fi. Okay. Now the second one is the viscous force. The viscous force, we know that how to get it, shear stress into area. Here the shear stress is developed due to the viscous force, and we know that the shear stress equation for a viscosity is a mu du by dy. Here du is the velocity change and y is the distance. Okay. distance between the layers of fluids, okay, vertical distance, okay. So here we can write the du is equal to velocity v and dy is equal to vertical distance L between the layer. So put the value in this equation du and dy. So mu as it is, area A is it is. Here du is equal to v and dy is equal to L. Now we have an equation of viscous force and inertia force. Now get the equation for a Reynolds number. So take the ratio of this both equation, okay. Now Reynolds number is equal to inertia force upon viscous force. So inertia force is equal to rho a v square and viscous force is equal to mu into velocity upon L into area. Now velocity and velocity is cancelled. L is go to the upside, okay. Now equation become the and area also cancel. So remains entity is a rho v1 means v and the length is come up, it's a L, okay, and in denominator only mu is there, vv is cancel, volume cancel, okay, and L is the move up, okay, in numerator, okay. So this is the final equation of Reynolds number rho VL by mu. In the case of pipe, the L is defined by the D is the diameter of pipe, okay, instead of L. In case of pipe, the Reynolds number is defined by rho VD by mu, okay. Now Reynolds number signifies the relative predominance of inertia to viscous forces occurring in the flow system. In short, we can say that the Reynolds number is very significant in the case where the inertia force and viscous force are importance in occurs in this system. Then Reynolds number is very significant or very important in the case, okay. Now this number is taken as a criterion of a dynamic similarity in the flow situation where the viscous force predominant. Examples are given where the Reynolds number is important. First one is the motion of submarine completely in a underwater, okay. Second one is the low velocity motion around the automobiles and aeroplanes. Incompressible flow through the pipes of small size and flow through low speed turbo machines, okay. So in all general cases Reynolds numbers are predominant or importance, okay. We can see from this examples. Now second one is the Froude's number, and we know that how to get the Froude's number. It's the ratio of forces. Froude's number is defined by the square roots of ratio of inertia force to gravity force, okay. The ratio of force in a Froude's is a inertia force to gravitational force and its under roots, okay, or square root, okay. The Froude's number is defined by the square root of ratio of inertia force to gravity force. Now we can find the equation of Froude's number. Then we know that we discuss in a Reynolds number, the equation of inertia force is a rho a v square, okay. Now Fg, the gravity force, okay. So we know that how to get the gravity force, mass into gravitational acceleration, okay. So equation of mass in form of density So mass equation or mass value is a density into volume, and gravitational acceleration is a g. Okay. Now volume is defined by L. Okay, then volume is defined by the L cube. So finally rho L cube g. Okay. Now L is subdivided as shown in figure, L square into L, and we know that L square is defined as a area. So rho A L G, rho A L G is the final equation for the gravitational force. Okay. Now we find the equation of Froude's number. So take the ratio and square root. In square root, inertia force and gravitational force. Put the value of or equations of inertia and gravitational force. So inertia force equation is a rho a v square, and gravitational force equation is a rho a l g. Okay. So rho a cancel, rho and a is a cancel, and remaining is a v square upon lg. So v square is out of under square root, okay, and in upon on square root lg. Okay, this is the equation of Froude's number. Now the Froude's number governs the dynamic similarity of the flow situation where gravitational force is most significant and all other forces are comparatively negligible. In short, we can say that where in the case the gravitational force is significant, in this system the Froude's numbers are important. Some examples for that in which the gravitational force are significant or Froude's number are important is the first one is the flow over the notch and varies, flow over spillway of dam, flow through open channel, considering waves and jumps, motion of ship in rough and turbulent sea. Okay. In all cases, the gravitational force are important or significant. So also the Froude's number are very important for these cases. Okay. Now next one is the Euler's number. It's all the ratio of forces, we know that. Which force is inertia force and pressure force. So Euler number is a square root of ratio of inertia force to pressure force. Okay. Now find the equation of Euler's number. Euler's number is defined by EU. Now we know that the inertia force equation is a rho a v square, and pressure force also know that the equation of pressure force, it's a pressure into area or intensity of pressure into area. Okay, pressure into area. Now Euler's number is equal to square root ratio of inertia force upon pressure force. Now put the equations of both forces, rho a v square upon pressure into area. Now here the area is a cancel and rho is come to the denominator, means the p upon rho as shown in slide. Now this is the final equation for a Euler's number, and Euler's number is important where in problem or situation where the pressure gradient or pressure force are significant or important. Okay. So some examples where the Euler's numbers are important are given. First one is the discharge through the orifice and mouthpiece and sluice. Second one is the pressure rise due to the sudden closure of valves. Third one is the flow through pipe. fourth one is the water hammer created in penstocks. Okay. Now these are the cases where the Euler's numbers are important, or we can say that the pressure force are significant. Okay. Next one is the Weber's number. It's also, we know that the ratio of force is, which force is? Inertia force to surface tension force. Okay. So Euler's number is the square root of ratio of inertia force of flowing fluid to surface tension force. Okay. Now get the equation of Weber's number. So we know that the inertia force equation is the rho a v square, and surface tension force is, we know that how to get surface tension into length. Now put the value of both forces, or put both the equations of both forces, rho a v square for a inertia force and for a surface tension force, sigma into L, surface tension into length. Okay. Now area is defined by the L square. Okay. So L and L is a cancel, and the remaining entity is a under root or square root rho into L into V square upon sigma. Okay. Now rearrange the equation as on slide, and this is the final equation of Weber's number. Okay. And Weber's number is very important in some cases or systems where the surface tension force are significant or importance. Okay. These some examples are given where the surface tension force are important or significant, and the numbers is very important is considered. Okay. The first one is the capillary movement of water in soils. Second one is the flow of blood in veins and arteries. Third one is the liquid atomization. So in all cases, the surface tension force are must significant to study these systems or analyze them. So in that case, Weber number must important for analysis of these systems or cases. Okay. Now next one is the Mach number. We know that it is the ratio of forces. Which forces? Inertia force to elastic force. Okay. Mach number is defined as the square root of the ratio of inertia force to elastic force. Now get the equation of Mach number. It is the ratio of square root of the ratio of inertia force to elastic force, and we know that the equation of inertia force, it is the rho a v square, and the equation of elastic force is the elastic stress into area. Okay. And elastic stress is defined by the capital K, and area is defined by A, and A is defined is also L square as a L square. Okay. Now the elastic force is defined by the K into L square. Now put the equations of all the both forces in this equation of Mach number. So in square root, inertia force equation is a rho a v square, and elastic force equation is a K into L square. Okay. Now area is also defined by the L square. So right, area is right as a L square. So L square and L square is a cancel in numerator and denominator. So remaining entity is written as shown in slide, and this is the final equation for a Mach number. Okay. And here in square root, K by rho is defined by the C, capital C, and it is the velocity of sound in the fluids or liquids. Okay. And Mach number is in short defined by the M is equal to Mach number is defined by the capital M. Okay, note that. So M is equal to V upon capital C. Okay, and capital C is under root K by rho. Okay. Now Mach number is important in some cases where the elastic forces are significant. The examples is the compressible flow problem at a high velocity, such as a high velocity flow in pipe motions and high speed projectiles and missiles. In that case, the Mach number is importance where the velocity is high. At that case, the elastic force are considered, and for the consideration of elastic force, the Mach number is important for that case or study. Okay. I hope you very well understand all kinds of numbers, importance numbers related to the model analysis and its mathematical equations and how to derive these equations. Okay. If any query related to this topic, then feel free to ask to me. Okay. Thank you again.